Okay, welcome. This is the first of two talks, and this first talk will work on deriving the PDE, or partial differential equation, for a random walk in one dimension. And what do we mean by random walk? So we're considering, let's assume that we have an individual, and we can use our imagination as to what this individual is, a particle, a human, an animal, something. And we're going to assume that this individual is walking along the x-axis and can only move either right or left. And without loss of generality, let's assume that this individual starts where x is 0. Okay, so let's just make this yellow individual there. Okay, and we're going to assume that in 1 delta t unit of time, the individual moves delta x units to the right with probability equal to 1/2, and moves delta x units to the left with probability 1/2. Okay, so we look at this individual. This person is basically flipping a coin each delta t unit of time and moving delta x units to the right with probability equal to 1/2, and delta x units to the left with probability equal to 1/2. And that's considered what's called an unbiased random walk. And it's unbiased because the individual doesn't necessarily give any preference to right or left. To derive a PDE for this random walk, we need to mathematize the ideas we've drawn here. So let's go ahead and put this here in the corner, and let's call P of x comma t the probability that the individual is at x at time t. Okay, so that's a probability, okay, and it's going to be give us a probability density function for each time t, and we condition then using the rules of the random walk above. Namely, if we look at the probability of being at x at some unit delta t into the future, well, what's going to happen? Well, either you were delta x units to the left at time t, or you were delta x units to the right at time t, and each one of those occurred with probability to 1/2. Okay, that's called using the law of total probability. Okay, so we make this plus sign probably a little bit better there. Okay? And then the next thing that we do is we do some sort of mathematical sleight of hand, and this helps a lot when you're deriving equations for systems here. What we do is we simply subtract p of x comma t from both sides. Now, unless you had some experience doing this, you might not know why you would, but once you see what happens when you assume that this is what to do, it becomes relatively slick to see, and maybe you'll try that with a subsequent model that you're trying to create. But if we do this, let's shrink this into the corner, then the left-hand side of the equation becomes p of x at t plus delta t minus p of x comma t is equal to, and then let's pull out 1/2 from everything. So if we pull out 1/2, and let's reorder things. So let's look at p of x plus delta x t. And since we pulled out a half from something that didn't have it, the remainder will have a 2 p of x comma t, and then finally plus p of x minus delta x comma t. And that whole thing gets put in those parentheses there. Okay, now the next thing again, and we didn't do anything other than rearrange terms here and pull out a half. The next thing that we'll do, again, seems like a sleight of hand until you see how useful it is. What we're going to do here is we're going to divide both sides of the equation by delta t. Okay. And then we're going to multiply both sides of, or the numerator and the denominator of the right-hand side by delta x quantity squared. Okay. Now if we do that, now we take our expression here and pull it in. The left-hand side here, if we allow our instance of time to become arbitrarily small, that's just the difference quotient with respect to t. So that becomes the partial of p with respect to t. And if we look at the right-hand side, if we group terms, so if we take these three terms here and group them with the delta x squared, this is the difference quotient for the second derivative of p with respect to x. Okay, and that's as delta x goes to 0 from above. So you're making your step size arbitrarily small as you're making your time frame arbitrarily small. And then lastly, we group the remainder of the terms. We take this 1/2 times delta x and group it with the delta t, and we assume that d is equal to that collection, and we are going to assume that that's constant as those two processes, the time scale and the space scale, go to 0. We're going to assume, like I said, that this is constant. And now we have this diffusion equation. For the random walk. Okay? And the only thing that's left to complete the problem is the initial probability profile for the system. And generally, if you look up here in the upper right hand corner, generally what we'll assume that is some Dirac delta function. And so usually we call it the Dirac delta function centered at 0, namely that you are extremely certain that initially you are starting at the origin, x is equal to 0. So that is your initial condition, which in PDEs we often call this f, although the Dirac delta function is not a function. Here we'll still call it 1. Okay, thank you.